Our human brains are wired to think linearly, because this worked well throughout most of our history. But nowadays, effects almost never have only one simple cause. The world has become highly non-linear. Let's examine our linear thinking. I fold a piece of paper. And then I fold it again and again. I can only fold it about 6 times, but imagine that I could fold it as often as I wanted. How many times would I need to fold a piece of paper to reach to the moon? What do you think? Write down your answer. The correct answer is 42 times. Did that surprise you? If you were close, then your brain is quite good at thinking non-linearly. Or you already knew the example. Most people think you'd need to fold a piece of paper like 1,000 or at least 100 times. This is not true because with each fold, the stack of papers doubles in thickness. It's a non-linear process. Actually, it's exponential growth. Here's another example. Here's a silicone straw. I flick it. What happens? It bounces back and forth. So here's the question. What made the straw bounce back and forth? Write down your answer. Now I take a spoon. I flick the spoon. Revisit your answer. Most people say something like, your finger made the straw bounce, or gravity. But when we see the example of the spoon, it becomes clear that this is too simplistic. Apparently, there is something in the way a straw is made up that makes it bounce when it's flicked. The elements in the system straw function together to make the straw bounce when flicked, while the elements in the system spoon have a very different reaction. And this brings us to the definition of what a system is. A system is a collection of elements that are tied together by relationships. Together they have a certain function. Around the elements is a boundary that is defined by the system's thinker. Outside of these boundaries there are external conditions. They influence the system, but they're not part of the intricate loops of the elements within the system. A system's function can be rather dull. But often a system's function is shaped by values and beliefs. For example, these two companies are systems that both sell toilet paper, but they have a very different function in mind. The elements of a system often span multiple disciplines. For example, a harbor is a business that functions within an economy. It has societal value. It's governed by laws. Behind the economy and society and laws, there are people with all their psychologies. Then there is the water that obeys the laws of physics. And there's the ecology in the water and on the land. So determining which element should be included in a system and where to draw the boundary often requires interdisciplinary knowledge. The specific relationships between elements usually requires more detailed knowledge of the functioning of elements within a certain discipline. As you already saw, the flow of information between elements is vital, and flows can be visualized in stock flow diagrams. A stock, such as the number of fish in the ocean, changes in response to the flows. New fish being born increase the stock of fish in the ocean, so it's an inflow. The dying and catching of fish decreases the stock of fish in the ocean, so they are outflows. Stocks often influence the flows, As there are more adult fish in the ocean, there will be more baby fish being born. So the stock of fish has a positive effect on the inflow. And as there are more fish in the ocean, ultimately there will be food shortages. So the stock of fish also has a positive effect on the outflow. The relationships between stocks and flows create feedback loops. More adult fish lead to more baby fish, which leads to more adult fish, which leads to more baby fish, etc., etc. This is a reinforcing feedback loop. And more adult fish leads to less fish food, which leads to less adult fish. This is a balancing feedback loop. Feedback loops can be visualized with causal loop diagrams. Which feedback loop is dominant at a certain time determines the behavior of the system. When a positive feedback loop is dominant, there is growth, and when a balancing feedback loop is dominant, there is a limit to growth. The relative strengths of interconnected positive and negative feedback loops can cause overshoot and collapse. Here you see an example from the 1970s where a group of systems thinkers designed the first computer model to simulate the state of the world. They simulated the growing human population and the food it requires and the resources. There was also a growing industry, which led to pollution. Because of the industrialization, the human population can grow very, very rapidly. It overshot its carrying capacity and then drastically declined. Nowadays, the state of the world is still being simulated, but with a lot more detail, by the Intergovernmental Panel on Climate Change, the IPCC. In these world systems, there is a natural component of the climate, the oceans and the living world, which are tied together mostly by the laws of physics. The natural world is affected by society, for example through consumption, pollution and the burning of fossil fuels. To predict the natural world, we need to just include the laws that govern the dynamics in the natural world as accurately as possible. For society, however, it's much more difficult to predict what will happen. For example, a new president can redirect the entire world onto a different path into the future. To consider societal changes, the IPCC uses scenarios. For example, there is a scenario where we keep doing sort of what we've been doing for the past decades, and scenarios where we adopt mitigation strategies and decrease our emissions. Simulating such scenarios can give you insights into how certain policy options can affect the state of the system in the future. And now another concept arises, and that is the concept of indicators. Systems often have a certain function or goal, which seems quite straightforward maybe on paper, but in reality systems might not function as well as they should. And indicators can tell you how well a system is living up to that function. A discrepancy in the perceived state of the system, which is indicated by the indicators, can inform action, for example, policy. So indicators should be well designed. The gross domestic product, or GDP, is often used as an indicator. It indicates how much money is flowing through a country's economy, but it's a very bad indicator for a country's well-being. Systems are often complex systems, where elements are interconnected and interdependent in a non-linear way. This is an interesting fact because complex systems have emergent properties. For example, complex systems can have multiple alternative stable states that can be possible just as well at the same time under the same conditions. And elements in complex systems can sometimes change unexpectedly rapidly, while all other elements are changing gradually. Complex systems can also show rigidity to change, which is also called hysteresis. And other emergent properties of complex systems are self-organization and the development of hierarchy. If you remember one thing from this lecture, remember this. At the core of systems thinking are feedback loops. Reinforcing feedback loops are often the easiest to spot in a system. Remember that these cause exponential growth. Since nothing can keep on growing exponentially, ever, there are always negative feedback loops that balance the positive feedback loops. If you spot a positive feedback loop, look for a possible balancing feedback loop and ask yourself, in reality, how strong are those possible balancing feedback loops relative to the reinforcing loops? And when will they become dominant? Will that be fast enough to prevent overshoot and collapse?